Hello, I'm Woobin, student of Gwangju University. We have studied the internal flow characteristics of the water meter by using the unsteady computational fluid analysis. The table of contents is as follows. Introduction. Flow meters are used in various fields such as general industry, petroleum, chemical, shipbuilding, medicine, food, steel, and semiconductor. In particular, various types of flow meters are used for flow control and fluid commerce in natural gas or water supply pipelines. There are over 100 types of flow meters in use today, and the measuring capacities range from seconds to seconds of seconds. The flow meter market in Korea is estimated at 120 billion won per year, including water meters and gas meters for home use and industrial processes flow meters, which account for 70% of them, are almost dependent on imports. For reference, the global market for flow meters is 305 trillion won. In addition, there are types of flow meters that measure the rotational speed in proportion to the flow rate by inserting a rotor such as an impeller into the flow field, such as a turbine meter, a water meter, or a PD meter, such as an overgear meter. All of these meters causes pressure losses and increase the uncertainty by reacting sensitively to changes in the flow rate distribution of the fluid entering the meter. Mechanical structures or rotating bodies installed in the fluid field are worn or damaged over time, so the flow meter characteristics change, requiring periodic calibration by the flow measurement standard system. The figure below is a typical water meter model used in Korea. Research method shown below is a 3D analysis model designed using the commercial software CATIA version 5. There are two models, FM1 and FM2. The flow direction is from the left side through the inlet and the blade to the outlet. The principle of operation is that the flow rate following through the inlet, the outlet, incline and rotate the blade and exits through the outlet. In the study, flow analysis was performed using Statistician Plus commercial software. The flow analysis of the water meter assumes unsteady turbulent flow, and the turbulence model for the flow analysis uses the standard K epsilon turbulence model. The fluid used in the flow analysis was water. To simulate the blade rotational movement of the water meter as the flow flows, the analysis was performed using the dynamic fluid body interaction function. The DFBI function can represent the motion of objects as 6 degrees of freedom when fluid momentum is applied, and can simulate the movement of a rigid body against pressures, shear forces, and other forces exerted by the fluid. This function was used to calculate the number of revolutions of blade and to calculate the flow trend at each flow rate and the flow rate distribution around the blade. The computational grid was created using the measure feature within the commercial software system plus. The number of grids generated was about 2 million FM1 and about 106 million FM2. The figure below shows the flow direction of FM1, FM2, and the generated grid, computational grid. Number 3, analysis result. The result of the analysis. The figure above shows the results of flow analysis inside the Flowmeter casing and around the blades when the inlet flow rate is 10 LPM. FM1 has a flow resistance in the stagnant section like the red box. In addition, the structure of FM2 simpler than FM1, but the blade side receives most of flow momentum and the remaining blades act as flow resistance. Following is the result when the inlet flow rate is 20 LPM. In the FM1, the flow momentum causes the blade to rotate well. The FM2 is supplied with momentum of flow only to some of the blades with the inlet and outlet inclined at approximately 15 degrees to the tangential surface. In this flow, the volume is generated in the conduit section of the blade inlet and outlet. These phenomena are expected to increase as the follow velocity increases, which may act as an obstacle to precise flow measurement at high flow rates. The following figure is a blade speed vector of the models for each flow rate. The flow rate of the FM1 is even and constant compared to FM2, and FM2 is biased in some place, resulting in an uneven internal velocity distribution. This may be due to the structure of the entrance and exit of FM2. The following is a graph of the rotation speed calculation for each blade. The average error of FM1 is 509% and FM2 is 16 or 8% based on the straight line passing through the origin. This is the result of analysis of the number of revolutions of the blade. FM1 FM is showing faster blade rotation. if the number of revolutions of the blades is high, relatively disadvantage, it equals the disadvantages. So durability life is shortened. Following is the static pressure distribution by model. The average FM1 has an even distribution of pressure drop by blade and input flow rate. FM1 has an even distribution of pressure from the inlet to the outlet, but FM2 shows sharp pressure drop at the inlet. The following graph shows pressure drop by blade by input flow rate. Pressure drop per inlet flow rate was measured similarly. The rotational speed of the blades is similar between the two models, but due to the structural difference of the water meter, the pressure drop is remarkable. This is analysis result of pressure drop of meter. FM1 has a low pressure drop, FM2 has a higher pressure drop. If the pressure drop is low, relatively, it equals advantage, reduced power loss due to low flow resistance. Conclusion. In this study, the flow characteristics, blade rotation speed, and pressure drop for water meters with different structures were calculated through the flow analysis, and the following conclusions were drawn. Number one, two water meter models with different shape structures were modeled using reverse engineering, and the flow characteristic and blade rotation speed were calculated by applying the FBI function to the inside of the Flowmeter and the blades. Number two, as a result of considering the internal flow characteristics, the flow rate of FM1 was evenly applied to the blade surface compared to FM2, and the flow momentum of FM1 generated the blade rotation well. FM1 blade rotation well, FM2 unevenly rotated. Yes. In FM2, the momentum of the flow is supplied only to a part of the blade, and the inlet and the outlet are inclined about 15 degrees to the tangential surface, and that volume is generated in the pipeline part of the blade inlet and the outlet. That volume is expected to act as a factor that inhibits precise flow measurement at high flow rate. Number three, as a result of flow characteristic analysis of the blade, the flow of FM1 was distributed evenly from bottom to middle and top part, while the flow of FM2 was unevenly distributed at all three positions. It is believed that this impedes the momentum of the blade and impairs the uniform uniformity of the rotational speed. Assuming that the blade's rotation speed is linear with the input flow rate, F1 shows an error of 5 or 9% and F2 shows a 16 or 8% error. Through this study, the flow trends of the two models with different shape structures were identified and the rotational speed was derived. The result of this analysis will be supplemented through future experiments and can be used as basic technical data for improving the accuracy of the flow meter. Thank you.